electrochemistry and a problem for it. So let's get this show on the road. First question, complete the standard reduction potential chart. For any problem that requires knowledge of reduction potentials, they'll give you a chart. It used to be that the AP exam would have a reduction table as part of its equation sheets. In addition to a periodic table, you had a reduction potential chart. Gold at 1.50, and here it is, our gold at 1.50, and then magnesium at a negative 2.87. Let's pull that chart up again. We'll run quickly down, and here's magnesium way at the bottom at a negative 2.37 volts. Now, this voltage is set up for 1 molar solutions and 1 atmosphere of pressure. But what's missing on this chart is that there's no voltage here for what can 1 molar hydrogen ions do. And the reason for that is that you should know that this is the standard. Everything is compared to 1 molar hydrogen ions and 1 atmosphere of hydrogen. Now, this is for the reduction, where we have this hydrogen ion, acid, pulling on some electrons, reducing to make hydrogen gas. Well, that is set up arbitrarily as 0. They said that's our standard. We're going to say the ability to pull in electrons by hydrogen ions is 0. And if you're better than hydrogen at pulling in electrons, like this gold is, it's 1.50. And if you're worse than hydrogen, magnesium certainly is at negative 2.87, then you're lower in the chart. So the negative value doesn't really mean negative voltage. It just means that it's worse than hydrogen ions. And as you saw that chart that I pulled up before, here's a list, and they happen to end up including hydrogen. Here's our hydrogen ions, and this is back on a 2013 AP chemistry exam before they changed it to the present system, and you would see that there's our 0, and here's our gold, which is like the 3rd best reducing substance in this list. Only fluorine gas and this cobalt going to cobalt plus 2 are better at pulling electrons in on this chart. For common materials, this gold is like the reducer, and this I just say this gold. I should say this gold ion, gold at plus 3, is the reducer, and here's our magnesium down here, pretty close to the bottom, lousy reducer. One warning, when they give you a chart, they may not put these in order. And my strongest piece of advice on any one of these questions that involves a reduction table, if they've got these things unordered or the negative on the top, reorder them, because you want to have this point of view of reduction. When I was in school, we had oxidation charts where this would be the loss of electrons, but now this is the standard reduction tables. And you should know hydrogen ions are listed at 0, not because they don't pull in on electrons, but just they're the standard that we do all our comparisons to. Just as you're expected to know that enthalpies of formation are 0, the Gibbs free energy of formation is 0, the reduction potential of hydrogen is 0. Now let's go on to the question. If a gold metal strip were placed in a 1 molar solution of magnesium nitrate, what would you expect to see happen in this reaction? We have gold, not gold plus 3, but gold, the metal, is placed in a solution of magnesium nitrate. That's not magnesium. This is the magnesium. What would you expect to see in the reaction? Our reduction tables tell us that gold plus 3 reacts to make gold. And magnesium picks up electrons to make magnesium, but gold plus 3 isn't in on this. And look at this, magnesium's so lousy at pulling electrons in, it's not going to take the electrons from gold. You see, here's our gold with electrons, and here's our magnesium trying to get electrons, but gold's up here saying, no way do you have enough reduction potential, enough ability to pull in on removing my electrons. In fact, this is why gold is such a marvelous material. Getting back to that chart, very few things that can take electrons from gold. It picks its electrons up and it holds onto them with a level of 1.5. So one of the ways for testing gold is what they refer to as a touchstone, where they rub a little bit of some jewelry on this rough stone, referred to as the touchstone. You just rub a small amount out. You won't see very much at all in terms of damage to whatever you're testing. And here's our site for the Gemological Institute of America, where they end up indicating how to use a touchstone to find out if you have pure gold or not. And the general idea is to put on a acid that can oxidize almost any material except for gold. And when you rub this off, if the gold is very pure, it's not going to oxidize. And if it isn't pure, then you're going to see some of this rubbed off material oxidize. I've got a link to this on the bottom of my webpage here, and you should check it out. It's a beautiful video on how to test for gold using oxidation and reduction. Well, back to our problem. Nothing can happen because magnesium can't pull electrons away from gold. Let's go here. We still have our gold, and we've got it in 1 molar hydrochloric acid. Well, hydrochloric acid is a strong acid, so we're dealing with this. Well, the ability of hydrogen ions, 1 molar, to pull in on electrons is 0. Our gold holds on to its electrons by 1.5, so nothing's going to happen. And that's why that touchstone works, because acids, except for one mixture of acids, a mixture of nitric acid and hydrochloric acid called aqua regia, can react with gold. And that's only because a complex forms. It's not an oxidation reduction thing. So we've answered our first 2 questions. We said, okay, these materials on the right of our reduction table, if they have a high reduction table, will hold on to their electrons. We've got these 2 taken care of. Our acid's going to just do nothing to our gold. So if you've got a pure gold ring, you can drop it in hydrochloric acid, and you can drop it in magnesium nitrate. Oh, magnesium nitrate. Magnesium ions are sort of interesting. Here's a website where they're selling a magnesium solution. And I found this one interesting because of the terminology they use. They said ionic liquid magnesium. And to a chemist, what do you mean? Ionic liquid? No. This is an ionic solution of magnesium that they're selling. They say it's magnesium chloride, which is soluble just like magnesium nitrate. Now they say that it has a picometer particle size. You say, well, that looks pretty scientific, but that's just because these are just ions in solution. If you were to look at ion size, here's a table of ion sizes with the radii in picometers, and indeed, magnesium is 78 picometers. Yeah, you're just telling me it's down to atomic size. And here's salt. I mean, you talk about a salt solution being liquid salt with picometer size. Let's get back to that ad. And it's ionically charged. Of course, you know, magnesium has a charge of +2. They're basically just selling magnesium ions in solution. And in this case, they're charging us $22 for a solution of magnesium chloride. We're going to go back to another solution that you can buy when we get to the next part of the problem. A, nothing happens because gold is not going to oxidize. B, nothing's going to happen. Gold is not going to oxidize. Take it from a touchstone. Now we've got magnesium metal. Magnesium ions pull in electrons to become magnesium, but the reduction potential is really, really low. It's not very good at that. It's really pretty lousy at holding on to its electrons. But here we've got a solution of gold 3 chloride. We've got our gold 3 ions. You can buy 5% gold 3 solution, 50 mLs for $335. You get about 2.5 grams of gold, which is about a gold. You've got to pay for them to dissolve it and somehow get it into solution. And again, they use aqua regia. Compare the $20 bottle of magnesium ions to the $300 bottle of gold 3 chloride. Very light yellow, and let's go to our problem. Magnesium metal, not good at holding electrons. Here we've got gold 3, which is extremely good at pulling electrons. It was at the top of the chart, so it will be able to pull electrons off this magnesium, which can't hold them on very well. The gold +3 will rip the electrons off this magnesium, and you will see the gold +3 turn into gold crystals on this magnesium, but it's not going to stay there long. This magnesium is going into solution, becoming magnesium +2, so those crystals will probably fall off. Now here's our general rule. If you have your reduction table in order, the ions or material, because this could be a gas too, that pulls in on electrons, which is higher, will win. It will go forward. And the material here will end up losing its electrons. It's going to go backwards. Its arrow is magnesium turning into magnesium ions. Let me flip back up here. We were talking about magnesium being such a lousy holder of electrons. There's something worse than magnesium, and that's barium underneath magnesium on the periodic table. A larger atom, it can't hold on to its electrons. They're in a further out shell. And here is, if you were to have a battle between barium, the metal, and magnesium ions, the magnesium will just barely win. This reaction will go forward. Our magnesium will start to corrode, and the final reaction will be the barium going backwards, turning into barium ions into solution. Magnesium going forward, making little crystals of magnesium. And here's our net reaction. In fact, magnesium ions reducing into the metal, and barium metal turning into barium ions. And again, our rule, the magnesium here is better at pulling an electron, so it does, and the barium loser ends up going into solution. Of course, that means with gold ions being this high on our table, that gold will be able to rip electrons off of almost anything. Here, any substance below our gold will be oxidized, will have its electrons ripped off. So if you have some iron, if you have some chromium, and if you have nickel, tin, lead, if you have copper, if you have even silver, the gold plus 3 will end up ripping the electrons off. So this gold solution is extremely corrosive. If you pour this onto a metal safe, it would dissolve, or I should say oxidize the metal, and form gold crystals, and you could get whatever is in the safe. But unfortunately, you'd have to spend a lot of money to be able to dissolve that safe door. But gold chloride, don't spill it on anything, because these gold plus 3 ions are ready to rip electrons off of anything, including your hand. We've answered this question. If gold solution was here, their plus 3 ions would rip electrons off of magnesium, and we know that from the reduction table. What about a battle between magnesium and hydrochloric acid? Well, again, that's our HCl. Here we've got a battle between H plus and magnesium metal. This gold, reduction potential of 0, it'll take the electrons from that magnesium and turn it into magnesium ions. So when this is all done, this metal magnesium will become a solution. You could sell it for $22 a bottle. But what do we get as a result? Well, the hydrogen picks up electrons and becomes hydrogen gas. So you get some real pretty bubbles of magnesium. And if you watch the little video of that happening, here's a video where you'd see this magnesium bar bubbling and bubbling away as hydrogen ions in this acid turn into hydrogen gas and go to the surface. The reduction of hydrogen and the oxidation of magnesium. That's it. We've answered the last question, and you should be able to manipulate and understand what's happening in a reduction table. These substances are good at moving forward if they're high up on the chart. And these substances to the right would be the ones who oxidize, and if something here is above this, the reaction will end up occurring. And you can figure it out using these beautiful reduction tables.